So hello everyone. So in this discussion is we will explore an important relationship between negation and the quantifier in logic. So the equivalence we want to prove is the negation for all x in a p of x is logically equivalent to the there exists x in a such that not p of x. But before jumping into the form of proof, let's think about a real life example. If I say it is not true that every student passed the exam, does this mean that the same as some students failed the exam? Yes, it does. The given states that negation for all x and a, p of x is equivalent to there exists x and a such that not p of x. So this equivalence shows that the relationship between the negation of a universal statement and an existential statement. So to prove this equivalence, we must show both direction of implication. So to prove the equivalence is we have to prove this too. The negation for all x and a, p of x implies that there exists x and a such that not p of x. And also we prove that there exists x and a such that not p of x implies not for all x and a, p of x. So it is important for us to prove both direction because logical equivalence works like a two-way street. If one statement implies the other and the other also implies the first, then the two statements always have the same truth value. So the first direction is slightly more involved and usually uses proof by contradiction. The second direction is very direct. If even one element fails p of x, then it cannot be true that every element satisfies the p of x. Statement number one is we state the given, which is the negation for all x in a p of x. So we begin with the information that it's not true that every element of a satisfies the p of x. This means that the universal statement fails, but we do not know yet which specific element caused the failure. So this sets the stage for a proof by contradiction. In statement number two is we give our assumption. Our assumption is that negation there exists x and a such that not p of x. So to prove the implication, we assume that negation of the conclusion. This means that we assume that no elements in a violates the p of x. In other words, we assume there is no x in a for which p of x is false. This assumption will be used to derive a contradiction. So in statement number three, it shows that for all x and a not p of x. So the reason of it is negation of existential quantifier from the statement number two. By logical equivalence, the negation of an existential statement becomes a universal statement with a negated predicate. Thus, if it is not the case that there exists x such that negation of p of x, then every x and a must satisfy the double negation of px. So in statement number 4 is we have the double negation from the statement number 3. So it states that for all x and a, p of x. So the expression double negation p of x simplified to p of x using the rule of double negation. Therefore, we reach the universal conclusion that every x and a satisfies the p of x. So in statement number 5 is negation for all x and a, p of x, and for all x and a, p of x. So the reason to it is the conjunction from the statement 1 and statement 4. So here is we combine the given statement from statement 1 and the conclusion from our assumption from statement 4. So this creates a direct contradiction. Statement 1 says that the universal claim is false. Statement 4 says that the universal claim is true. So a statement cannot simultaneously be true and false, so we obtain a contradiction. And statement number 6 states that there exists x and a such that not p of x. So the reason is true proof by contradiction from statement number 2 and also from statement number 5. Since assuming that the negation of our desired conclusion produces a contradiction, that assumption must be false. We conclude the original implication must be true. There exists some x and a such that negation of p of x, so this completes the first half of the equivalence. For the proof table number 2 is we have to prove that there exists x and a such that not p of x implies negation for all x and a, p of x. So as you can see in statement number 1, there exists x and a such that not p of x. So we begin by acknowledging that at least one element in A does not satisfy P of x. This element acts as a counterexample to the universal claim all x in A satisfy P of x. Statement number 2 is we give our assumption. So our assumption is for all x in A, P of x. So we now assume that the opposite of the conclusion we want to prove. So we assume that every x in A satisfies the P of x. So this sets up another proof by contradiction. Statement number 3 is negation of P of x. So this came from the given which states that some x does not satisfy the P of x. So the given essential statement tells us there that at least one element for which P of x is false. This directly contradicts our assumption that all elements satisfy the P of x. In statement number 4, it states that negation for all x in A P of x. So the reason is negation of existential quantifier from the statement number 3. Since our counterexample exists, the universal statement all x satisfy P of x cannot be true. Therefore, we reject x. And statement number 5 states that there exists x in A such that not P of x and negation for all x in A P of x. So the reason is the conjunction from statement number 1 and statement number 4. So here is we combine our given essential statement with the negation of the universal claim. So this verifies that the existence of a single violating element disproves the universal statement. And statement number 6 states that negation for all x in A P of x. So the reason is through the proof of contradiction from the statement number 2 and the statement number 5. So our assumption that all elements satisfy P of x contradicts the given information. Thus, the assumption must be false and we can conclude that the universal statement cannot hold.
So in conclusion, the two statements are equivalent because saying not all elements satisfy P of x means there must exist at least one element does not satisfy P of x. Likewise, if even one element fails to satisfy P of x, then the universal statement all elements satisfy P of x became false. Therefore, both statements describe the same logical situation, making them logically equivalent. So that's all for the discussion. Thank you.
Good day everyone. Welcome to our LE1 group presentation. Today I will discuss about the topic 2, set theory on sets, equivalence relations and function, problem set number 5. I am yours truly, Christian Cordano from group 9 2SM. To ensure that our presentation will have a smooth flow, we will follow the table of contents. First is the introduction of the problem. Second is the definition of injective function. Third is the proof of injective function. Fourth is a definition of surjective function. Fifth is the proof of surjective function. And lastly is the conclusion. Topic 2, problem set 5 wants us to determine whether the function f from the natural numbers to the natural numbers defined by f of n is equal to n squared is injective or surjective. But first, what is injective function and what is surjective function? Injective function is also known as one-to-one function. A function is injective if each element of the range corresponds to only one element of the domain. In simpler terms, no two different inputs give the same output. If a function is injective, it should satisfy if f of a sub 1 is equal to f of a sub 2, then a sub 1 is equal to a sub 2. So now we will determine whether the function is injective. Assume that f of a is equal to f of b for some a and b is an element of the set of natural numbers. Recall that the domain and range is a set of natural numbers which contain the elements 1, 2, 3, 4, 5, and any other positive whole numbers. So back to our function. Function is f of n is equal to n squared. Therefore, f of a is equal to f of b becomes a squared is equal to b squared. Taking the square root of both sides becomes a is equal to negative and positive b. However, the domain and range are natural numbers. Therefore, our a and b should be non-negative. So we will ignore negative b. This remains as with a is equal to b. This shows that f of a is equal to f of b, then a is equal to b. Therefore, the function is injective. Next, we will define surjective function. Surjective function is also known as onto function. A function is surjective if every element of the range is the image of some element in the domain. In other words, every possible output is actually achieved by some input. So now we will determine whether the function is surjective. We will use proving by counterexample. Consider the number 2. 2 is acceptable as an output because it is an element in the set of natural numbers. But my question is there a natural number n that satisfies n squared is equal to 2? None, right? Because the only value that can satisfy n squared equals 2 is the square root of 2. But the square root of 2 is not a natural number. Since there is an element in the range that is not an image in any elements of the domain, therefore the function is not surjective. In conclusion, the function f from the natural numbers to the natural numbers defined by f of n is equal to n squared is injective but not surjective. And that ends my presentation. I hope you learned something. Thank you for watching. Again, this is Christian B. Cordano. Next, to present the topic 3 is Miss Catherine Lauron. Give her a round of applause.
Hi everyone, I am Catherine Lauron and I am from Group 9, and in this video I will be discussing problem set number 3, specifically the question number 3. So the question is to determine whether the omega is a successor ordinal or a limit ordinal. Let's start first by recalling the definition. So a successor ordinal is an ordinal that can be obtained by adding one to another ordinal. So an ordinal alpha is a successor if it can be written as alpha equals beta plus 1 for some beta. A limit ordinal, on the other hand, is an ordinal that is neither zero nor successor of any ordinal. Now, omega represents the set of all natural numbers such as 0, 1, 2, 3, and so on. It is the smallest infinite ordinal and is greater than all finite ordinals. But here's the key point. There is no largest natural numbers because of that. There is no ordinal beta such that omega equals beta plus 1. In other words, omega is not the successor of anything. Therefore, omega is a limit ordinal. It serves as the limit of finite ordinals, but it does not have an immediate predecessors. And that concludes my discussion. Thanks for watching.